So we were talking about the beta distribution and the gamma distribution separately, and I mentioned that they're connected, but we haven't seen how is beta connected to gamma other than being consecutive letters of the Greek alphabet. So there's one very, very famous example that connects the beta and the gamma in a very neat way. So that seemed like a natural starting point to bring the beta and the gamma together. Another thing we haven't done yet is figure out the normalizing constant for the beta distribution, except in the special cases where we could use Bayes' billiards arguments. So we want to have the normalizing constant in general for beta and gamma. Okay, so this is an example. I mean, it's a story that connects the beta and gamma. I call it the bank and post office. You can call it whatever you want, but that's just I just like having a concrete example in mind. And for some reason, I call this the bank post office example. So the idea is you have to go to the bank and do something. You have to go to the post office and do something. Both of them you have to wait in line for some amount of time. And let's define some notation. So let's say first you go to the bank and you wait for a total of X minutes to be served. And suppose that X is gamma of A lambda. So the interpretation, if A is an integer, there would be I didn't just like randomly write down gamma. There would be a natural interpretation here. If A is an integer, let's say gamma of 5 lambda, remember we saw that gamma of 5 lambda, you can think of it as the sum of 5 IID exponential lambda. So that would be like the assumption that there's 5 people in line before you, and each of them takes an exponential lambda amount of time to be served, and there's only one line, you wait in line, and then eventually your turn. Okay, and then let y be gamma of b lambda, same thing. X is how long you wait, that's your waiting time to be served at the bank, and y is your waiting time at the post office. And we'll assume that they're independent. X is independent of y. That's the assumption. All right, so that's the statement of the setup. Now the question is, first of all, what's the distribution of your total waiting time? And let's call that t for total. And that we already actually know, at least for the integer case, right? This is a sum of, if a and b are integers, this is a sum of a IID exponentials. This is a sum of b IID exponentials. So together they must be a plus b IID exponentials. So just from that story, you can immediately say that it's gamma a plus b lambda, and we don't have to do anything else. If it's not an integer, you could just do the MGF that we also did and just multiply the MGFs. And again, that will confirm gamma of a plus b lambda. All right, so that was easy. We didn't need to do anything. But suppose we also, another natural thing to look at is the fraction of time. That's just, of your total waiting time, what fraction of that was spent waiting at the bank? That's another natural thing to look at, right? So I'll just call this thing W just to have a name for it. So I want the distribution of these two things, not just one. Since there's two of them, actually what we want is the joint distribution. We already know that the marginal of this is gamma a plus b lambda. We don't yet know the distribution of W, and we don't yet know the joint distribution, okay? So you might think to yourself a little bit, if you had to guess, do you think that the total time spent waiting is independent or dependent of the fraction of time spent waiting at the bank? So do you want to guess? How many of you think that they're independent? Okay, just guessing. And how many of you think they're dependent? Okay, pretty close. It's not obvious. At least I don't think it's obvious. So we have to do a calculation to find out, because I don't think it's intuitively obvious one way or the other whether they're independent or not. They don't look independent because you have the x plus y here, But on the other hand, just knowing how long you waited, what does that tell you about the fraction? So you can make an argument either way. It's not going to resolve the question. All right. So let's actually let lambda equal 1, just to simplify notation. It's not really any harder with general lambda, just more notation floating around. For the general case, anyway, we talked about the fact that you could go from gamma A1 to gamma A lambda just by dividing by lambda. So at the end of the day, if we want to put lambdas back, we could put lambdas everywhere. It's not going to affect W because you're kind of scaling everything by the same factor. It's going to cancel out anyway. And then this one would be gamma A plus B lambda instead of gamma A plus B1. It's just a scaling thing. So this doesn't really lose any generality. All right. So now we just find the joint PDF. Okay, so here's the joint PDF. F sub TW of TW equals, so we're going to start with the joint PDF of X and Y, and then we need to adjust it by multiplying by this Jacobian, so we're going to have to do a Jacobian. We're not going to do a lot of Jacob. Probably this is the last Jacobian I'll ever do in lecture, but we do need one here, so there's going to be this Jacobian thing, dxy dtw. So we just need to compute these things and then simplify, okay? So first of all, the joint because I assumed x and y are independent, the joint PDF of x and y, we just multiply the PDF of x times the PDF of y. So that's very straightforward. It's just a gamma, 1 over gamma of a. I'll just put the two normalizing constants here. Those are both gammas. Remember, the gamma PDF is x to the a, e to the minus x. And then we have the one for y to the b, e to the minus y. And then there was an extra 1 over xy, just in the gamma PDF, times this Jacobian thing, which we'll fill in. All right, let's do the Jacobian. So our here the transformation is written with capital letters, but let's write the corresponding thing with lowercase letters. That is, we have x plus y equals t, and we have x over x plus y equals w. And I think it's a little bit easier if we invert this and solve for x and y in terms of t and w. And that's not hard to do, because notice from this second equation, that's just x over t, right? The denominator is t. So x over t equals w, so x equals tw. So that's just easy algebra. And let's solve for y. If we take 1 minus this, we'll get, take 1 minus on both sides. So I'll just write that separately. Y over x plus y equals 1 minus w. I just took 1 minus on both sides. But that's just y over t. So y equals t 1 minus w. So that's what the transformation is in the other direction, right? So, okay, now we just need to do a 2 by 2 determinant. We take, this notation means take the derivatives of x and y with respect to t and w. So let's start with the x, take the derivative with respect to t, and we'll get w. Take the derivative with respect to w, and we'll get t. Now go to the y, take the derivative with respect to t, that's 1 minus w, and then the derivative with respect to w, that's really just t minus tw. Derivative with respect to w, I'll just write that down, t minus tw. Now we're taking the derivative with respect to w, so we're treating that part as a constant, and so then we would just have minus t. Okay, and then we're doing the determinant, that times that minus that times that. So that's minus tw, and then minus t times 1 minus w. And so it's minus tw, and it's minus minus tw. Tw's cancel. The only thing that's left is this minus t. So the Jacobian simplifies really nicely. It's just minus t. All right, so and then in the Jacobian formula, we're actually doing these absolute value bars here are kind of serving a double purpose. That means take the determinant and then take the absolute value. So sometimes you might see it written with like double or little bars like that, which looks kind of ugly, but just to remind you, take the determinant, take the absolute value. We don't want a negative PDF. So that's just t here. So I don't really need to write these absolute value signs. T is positive, so we're using t, not minus t. All right, so now we have the joint PDF. The only thing we have to do that's left is to write this in terms of t and w, because we still have x's and y's here. So I'm just going to plug in the definition of x and y in terms of t and w. So x is tw. So that's let's just write the w stuff first. So that's w to the a, and this one y. I'm just plugging in what I wrote for y there. That's 1 minus w to the b. Then we also had, because it was tx, we have t to the a, t to the b. So that's t to the a plus b. Exponentials is e to the minus of x plus y, but x plus y is just t. So that's e to the minus t. So this is starting to look like a gamma PDF. And then this stuff at the end, x, well, let's see, x is tw. So we're going to have, and this has a t, so we're going to have a 1 over t, because it's t over t squared. And then we also have an extra w and an extra 1 minus w. So we'll just write it like that, a minus 1 and b minus 1. And is that everything? We can put a 1 here. So I was just trying to write it as a function of w times a function of t. I was trying to do that, but actually I did do that. So that's a function of w times a function of t, therefore they're independent. Not at all obvious, but now we just proved that they're independent. Okay, well the next question is, what's the PDF? Well, this is exactly the gamma. We already knew this was a gamma a plus b lambda, and this confirmed that. The only thing that's kind of weird about this is we don't have the normalizing constant. And I was just discussing this in office hours Wednesday night with a couple of people who are, like, where's the normalizing constant? And my answer is, if you don't see the normalizing constant, you can always just multiply by 1, right? So I'll just put it there, gamma a plus b. Well, of course, I can only do that if I multiply and divide by the same thing, so I'll put back gamma of a plus b here. Writing it this way, now this is exactly the gamma of a plus b1 PDF. All right, so some conclusions from this. First of all, they're independent. Secondly, let's find the marginal PDFs. If we integrate this thing, let's get the marginal PDF of W. So remember, to get the marginal PDF, we just integrate the joint PDF. And that's actually an easy integral. So we're just going to integrate this joint PDF dt, right? Integrate out the t, then we'll get the marginal of W. But that's an integral you can do in your head, so I'm not going to rewrite this whole thing. Because imagine sticking an integral sign here. We're integrating dt, so this whole thing, this is a function of W. So since this integral is dt, you just take out this entire function. It's just serving as a constant. All we're left with then in the integral is the integral of this. That's the gamma PDF. We already know it integrates to 1. So the integral is just gamma of a plus b over gamma of A, gamma of B, W to the A minus 1, 1 minus W to the B minus 1. As a consequence of that, we've actually just derived the normalizing constant of the beta. It has to be this. Notice that this is a beta AB up to a constant. We didn't know what the constant was yet. Now we know what the constant is. Because if this were the wrong constant, then this would not be a valid marginal PDF. But we just proved that this is the marginal PDF. If it's the marginal PDF, it has to integrate to 1. So that's the normalizing constant of the beta. Okay, so in particular, this tells us, first of all, now we know the normalizing constant of the beta. It didn't look like we set out to, a lot of times in math you kind of just discover something that you're not trying to do. You can't solve a problem, so you try to solve some other problem, and then you can't solve it, but you learn something else. It's like that here, like, we're just like, this is a pretty natural problem with gammas. If you just try directly to find the normalizing constant of the beta, you're faced with a very difficult integral. In this case, we just happened to notice that the marginal was beta, and we got this normalizing constant for free, essentially. And we also know that T is gamma A plus B 1, and B is beta AB, W, that is beta AB, and they're independent. So that's a very special property of the gamma and beta, how they fit together in that way. Actually, I mean, there's a theorem that essentially says if you replace this gamma by any other distribution, these will not be independent anymore. So this is a very special, that's hard to prove, but that happens to be true. This is a very, very special property of the gamma and the beta. Okay. So just as an example of how you might use this, which actually relates to the next homework. In general, so suppose we want to find the expected value of W, where W, using the same notation, W is beta AB. There's two ways to do it. One would be to use Lotus. And I'm not going to write out the Lotus right now because that should be, automatic, unconscious by now. Hopefully you could all write down the Lotus really easily, and you can visualize what would the Lotus look like. Well, it just means you're integrating, well, it's not even Lotus, it's just the definition. But in fact, if you wanted E of like W to the 12th or something, that's going to be just as easy, just using Lotus. But just for the mean, you'd write down the PDF times W, right? So that would just become W to the A. But that still looks like a beta, right? So once you're comfortable with, the pattern of the beta distribution, you can just write down the answer, because as long as it's W to a power 1 minus W to a power, it's still going to look the same. If you want the expected value of W to the 100th power, it's not any more difficult, because then you're just adding 100 up here, but it still looks the same. So once you understand what the beta distribution looks like, then you can do it that way. So that's one way to do it. I'll also just say Lotus / definition. But here's a cooler way to do it. I'm going to interpret, I drew a line here, which means that problem was over, and we're starting a new thing here, and we just have W as beta AB, and we've forgotten all the stuff above the line. But we can remember the stuff that was above the line. That's okay, right? Because the expected value, that's what it means. A distribution has to have if it has an expected value at all, it has to be some well-determined expected value. It's not like you do this with one particular beta random variable and you'll get one thing, and you do it with another one, you'll get another thing, right? If you have a beta random variable, there is a well-defined thing. So I can choose my favorite way to generate a beta, all right? I can choose any way I want, as long as it's beta AB. Well, this right here is my favorite way to generate a beta AB, so I may as well choose that one. So now, even though this W didn't necessarily have to have that interpretation, we can choose to give it that interpretation, because that won't affect the expected value. So if we interpret it that way, we have E of x over x plus y equals E of x over E of x plus y, not by linearity, that's not linearity. This is actually one of the most common mistakes in probability, is to write this kind of thing without justification. So you have a homework question about this. Usually, if I write E of something over something is E of the numerator over E of the denominator, usually that's completely wrong. So I'll just say, be very careful. This is a special property. I'll show you why this is true in this case. I'm using the same notation as up there, so I'm not going to rewrite all the notation. That is, that's gamma A1, and that's, gamma B1, same notation. Usually this would be a horrible, horrible blunder. In this case, this is true. The reason that is true is that, so why is that true here? Y is E of x over x plus y. Let's write it the other way. Put the E of x plus y on the other side of the equation. E of x in this special problem, I'm not saying this is always true, in this special problem of gammas, and I'll just call it the gamma beta or the bank post office. Well, usually this is wrong. However, we have a very important fact there, which is that t was independent of w. So we know that x over x plus y, for this particular problem, is independent of x plus w, x plus y, right? The fraction is independent of the denominator, independent of the total. Therefore, they're uncorrelated. Independent implies uncorrelated. Definition of uncorrelated for two random variables x and y is that E of xy equals E of x, E of y. So that says uncorrelated. This being uncorrelated of this just says that this times this is E of this times this, but when you multiply x over x plus y by x plus y, you get x. So it's true because they're uncorrelated. Oh, by the way, I mean, that tells us the answer is just a over a plus b, because we already know that the mean of the gamma a1 is a, and you could use linearity in the denominator, or use the fact that that's gamma of a plus b1. Okay, so the expected value of a beta is a over a plus b, beta ab. Similarly, you can get the variance or various other functions of the beta. Okay, so those are the main things about gamma and beta. So let's go on to our next big topic, which is order statistics. I tried thinking of a good segue from beta to order statistics, but it's closely connected, but you won't see why until we get to the end of order statistics, not the beginning of order statistics. The beta will come up again, though, so don't worry. You haven't said goodbye to the beta forever. All right, so let me tell you what order statistics are. We've already seen some order statistics. You had a difficult homework problem about the maximum and the minimum. Meant to be difficult, but meant to make you think, right? Like one key insight from that is that the covariance of the max and the min is not the covariance of x and y. You can't make the argument that one of them's the x and the other one's the y and so on. So that was meant to get you to start thinking about order statistics. This is going to be the more generalization of that kind of thing with the max and the min. So if we have random variables x1 through xn, and let's assume that they're IID, and this is just the definition right now. Order statistics means we put them in order, and then those are the order statistics. Which sounds pretty simple, but you really have to think carefully about what does it actually mean to do that. That is, hopefully for the homework and other stuff with the maximum and minimum, you started thinking about what does it actually mean to think of the max xy as a random variable, right? Anyone can take the maximum of two numbers, just take the bigger number. What's the maximum of two random variables? That's a random variable, and hopefully you've thought by now about what that actually means, but I'll talk about the more general version here. The order statistics are x1, this is just notation, x1 less than or equal x2 less than or equal blah, 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 less than or equal to xn. So we put, this is standard notation where you subscript them with parentheses, where this notation means that x1 is the minimum, right? And then x2 is the second smallest, x3 is the third smallest, and so on, all the way up to xn. Let's put xn, yeah, all the way up to xn is the maximum. So those are the two extreme order statistics, the max and the min. But then we have everything in between is also of great interest, right? For example, the median, right? Median is a familiar concept. That's just, take all these values, take the one in the middle. So there's some ambiguity about how to define median if n is even, which is not really relevant for our purposes here. So, but if n is odd, and let's say you had 5 numbers and you asked for the median, it's just the middle number. That would be the third one, right? So the median is x sub n plus 1 over 2. That would be the middle number. If there's an even number, different people use different conventions. The most common thing would be to take the two middle numbers and then average those. But anyway, point is, we can get the median. We can get other percentiles, or what's called a quantile, and so on. Quantile, just think of percentiles. Like you can find the one that 75% of the observations are below that point. That kind of thing. Median is right at the middle, at the 50th percentile, right? So okay, so those are the order statistics, and there's a huge literature on order statistics, a huge amount of applications of order statistics in statistics, because it's just a natural thing that a lot of times you have data and you don't necessarily care about, the data might have come to you independently in this particular order, but that you may not care about that, and often you want to rank things, right, and look at the largest, the smallest, the middle value, things like that. Interquartile range is a famous concept in statistics. That just means take the 75th percentile minus the 25th percentile, things like that. All kinds of statistical quantities are defined in terms of order statistics, so we want to be able to say something about their distribution. That's actually a pretty hard problem, though. The main reason that they're difficult to work with, since they are dependent, even though that's the key insight, one key insight about order statistics. In fact, they're going to be positively correlated. Even though we started with IID, they're still dependent. Why? Well, it's like you saw in the homework. The maximum is always bigger than the minimum. So if you know that the minimum is really big, that forces the maximum to be even bigger. And that same argument extends to any, if I tell you x, the third order statistic, well, the seventh order statistic is even bigger than that. So they give you information about each other. So we have to be very careful about that dependence. And also they're tricky in the discrete case. So we're mostly going to assume the continuous case. Discrete case, we have to worry about ties. That is, two random variables being exactly equal. That's a serious issue in the discrete case. In the continuous case, which we're going to talk about for the rest of today, then we don't have to worry about that issue because the probability is 0 that two continuous random variables will be exactly equal to infinitely many decimal places. Okay, so now let's assume that they're continuous, and let's derive the distribution of one of the order statistics. Okay, so let's let x1 through xn be IID continuous. Let's say they have a PDF little f and CDF capital F. And we want to find the CDF and the PDF of the jth order statistic. CDF and PDF of xj with parentheses. Okay? So just for getting the maximum and the minimum is not too difficult, and you've already done similar sorts of problems before. Like if you say that the maximum is less than some number, say 10, that's the same thing as saying that they're all less than 10, and then you use independence. But we want to get any of them, right? Any xj. This is going to be the marginal right now. So another since they're dependent, we would also like to know the joint distributions. But let's focus on the marginal for now. All right, so let's do the CDF. So we want to know what's the probability that xj is less than or equal to some number x. Definition of CDF. And I find for working with order statistics, it really helps to draw a picture. So we just have a number line. We have some number x, and let's just interpret this event in terms of a picture. This says that the jth order statistic is to the left. Maybe it's over here somewhere. And of course, the other order statistics like xj minus 1 are even smaller. So maybe x1 is over here, right? So the first j order statistics all have to be to the left. Now, it could be that xj plus 1 is over here, and it could be that's over there. We didn't specify, right? So I'll say here that there may be more. We could draw two pictures, one where actually xj plus 1 and xj plus 2 and xj plus 3 are over here, and finally xj plus 4 crosses over x. Or we could draw another picture where xj plus 1 is already to the right of x. Either way, this event has occurred. So in words, just by looking at pictures like this and then interpreting it in words, notice that saying that the jth order statistic is less than or equal to x is exactly the same thing as saying that at least j of the let's say xi's are less than or equal to x, right? Because we need to have j of them to the left, maybe more than j, that's okay, right? But at least j. So that's exactly the same event. Now we can actually just write down a formula directly. If there's at least j of them, let's actually specify it more and say, how many are there? Well, let's suppose there are k of them. So k goes from j to n. So I'm just going to break this up into disjoint cases, where the cases are counting how many of these x's are to the left of little x, right? Just breaking it up into cases. Okay. So assume there are exactly k. What's the probability of that happening? Let's say it a different way. What's the distribution? It's a binomial distribution. How are you defining your success? Success means to the left of x. Failure means to the right of x. So this says this is at least j successes, but we're going to sum that up over exactly k successes. K goes from j to n. So it's just a binomial. And choose k. The probability of success is probability of being to the left of x. By definition, that's just the CDF. So this is f of x to the k 1 minus f of x, that's the probability of failure, to the n minus k. So that's the CDF. Now, of course, once we have the CDF, we can get the PDF by taking a derivative of this, but that's going to be this big, ugly sum. And I'm too lazy to try to simplify that sum. So let's do the PDF a different way. You get the same answer. It just takes some work to deal with that sum. So I'd rather think more directly. All right, so here's the PDF. How do we get the PDF? Well, we're just going to draw a picture and think about what it means. All right, here's the picture. PDF of xj, let's call it f sub xj, PDF x equals, and let's just write down the answer, because that's a nicer way to do it. So here's x. We want the PDF at x. Now we have to be a little bit careful that density is not a probability, like the density could be greater than 1 and all that. But we talked about the fact before that if you take a PDF and multiply by some tiny increment, then that's essentially the probability that the random variable is in a tiny interval of that length. That is, imagine this tiny, I'm drawing the interval big enough so that you can see it, but imagine that this is a tiny, tiny interval of length dx. So it's infinitesimally small, okay? And so we're actually going to look at f of x dx as we're just multiplying by the width of that interval, and then we're letting it go to 0. We're letting it become, taking a limit, essentially. Now we can interpret this as saying the probability that the jth order statistic is in this tiny interval, okay? Now let's just think about how could that happen? Well, first of all, it means that one of these observations must lie in this tiny interval. So we'll take n. There are n choices for which one. That is, this could have been x. One of them has to be here, right? Good chance to use the pink chalk again. One of them has to be like right here, somewhere in this tiny little interval. There are n choices for which one goes there. Now assume that that has probability f of x dx of actually happening. Okay? Then let's look at the rest. There are n minus 1 observations left. This is supposed to be the jth order statistic. So that means there must be j minus 1 of them to the left. Right? J minus 1 of them are anywhere to the left of this tiny, tiny interval. One of them is in this interval, and then the rest of them are to the right. So that's n minus j of them. Now we chose one of them that went right there. We need to choose which ones are to the left. So there are n minus 1 left to choose from, and we can choose any j minus 1 of them. Then we just need to know what's the probability that those specific j, now you can imagine that we chose a specific set of j minus 1 of these observations. They all need to go to the left. So it's just f of x. That's the probability of being to the left of x to the j minus 1 times 1 minus f of x to the n minus j, because these n minus j need to be to the right. So just to simplify this a little bit, that the PDF is n times n minus 1, choose j minus 1, f of x, capital F of x. It's kind of a neat looking formula because it involves both the CDF and the PDF. So the CDF to a power, 1 minus the CDF to a power, and the PDF. You could also take the derivative of this and you'll still have a sum, but if you do some algebra on the sum, it'll simplify to this eventually. Okay, so that is the marginal PDF. I was tempted to put on the homework a similar problem with the joint PDF of two-order statistics, and I still think that's good. I didn't put it on the homework, but I still think it's good practice. Maybe I'll put it on the strategic practice. I haven't posted the next strategic practice yet, but I'll do that sometime tonight. Maybe I'll put this on it, maybe I won't. But what I'm trying to say is, what if you wanted the joint PDF of like X, the third order statistic and the seventh order statistic? You could draw a picture like this, except that then you have to say, okay, you kind of have two of these infinitesimal intervals, and you do an analogous argument. You could get the joint PDF that way. There's other ways to do the joint distributions too. In Stat 110, we're mainly, for the order statistics, we're mainly concerned with the marginal ones, as long as you keep in mind that they are dependent. Okay, so let's do a quick example. The easiest example to think about, but it's also a very useful example just to have in mind, is the uniform order statistics. So let's let U1 through UN be IID uniform between 0 and 1. And we want to find the distribution of the jth order statistic. So F sub Uj of X, the PDF of the jth order statistic. Well, I'm just going to apply this result. Okay. Well, that just says n times n minus 1 choose j minus 1. F of x, remember that the CDF for the uniform just increases linearly because the PDF is a constant. So that's just x to the j minus 1, 1 minus x to the n minus j. And the PDF is just 1, at least this is for x between 0 and 1, 0 otherwise. Well, that should look kind of familiar, right? X to a power, 1 minus x to a power. I don't even care about this constant. I mean, the constant is just whatever it has to be to make it integrate to 1. And you can check that this is consistent with the constant we derived earlier. But the key part of this is this, right? It's a beta. So we know that U sub parentheses j, the jth order statistic, is beta j n minus j plus 1, which relates back to something we did a while ago with the expected difference between two uniforms. So we did this calculation when we were doing 2D Lotus, the expected value of U1 minus U2, right? And I drew this little picture here, and I said, okay, one of them could be there, one of them could be there, 1/3, 2/3. So on average, the difference would be 1/3. So, okay, so what was I really doing? Well, another way to say this is that the expected value, the absolute difference is the max minus the min, as you were thinking about on the homework. So that's the expected max of U1, U2, minus the expected min of U1, U2. But according to this, the maximum is distributed as beta of 2, 1. And the minimum is distributed as beta of 1, 2. So this has mean 2/3, and this has mean 1/3 equals 1/3. So that just confirms the earlier result that instead of having to do a 2D Lotus and things like that, we just say, oh, we recognize this as a difference of two betas. The max is not independent of the minimum, but linearity always holds. So that's nice. All right, one last thing, just to give you something to think about over the weekend, if you don't have enough to think about. So our next big topic is conditional expectation. In a sense, you already know what conditional expectation is if you understand conditional probability, because it just means take expectation using conditional distribution rather than using the distribution. So for example, we're going to use this notation like E of x given A, where A is an event. And on Monday, I will talk more about what this means, but I claim that this is something that you should already understand because it just says use the conditional distribution given A, right? So it's basically something we're already familiar with, but I will go into a lot of detail about its properties. For example, we can say that E of x equals E of x given A, P of A, where A is any event, plus E of x given A complement, P of A complement, which looks completely like the law of total probability, right? Except that we're using expectation instead of probability. And like in the discrete case, just to quickly, see how would you prove something like this. In the discrete case, we'd have the expected value is the sum of values times their probabilities. All we would have to do is expand this using the law of total probability. That is, we break this up into two terms, and then just break it into two sums, and you get this. So this is a pretty intuitive formula, I think. We'll go into more detail about it. It's just the expectation version of the law of total probability. All right, so one quick little puzzle for you to think about. This is called the two-envelope paradox. And I think this paradox is much more deserving of the name paradox than like Monty Hall. Luckily, people don't usually say the Monty Hall paradox. But if they did, this one is more deserving of the name paradox. Here's the problem. I'll just tell you the problem quickly. We won't try to solve it today since there's not time. But anyway, it's fun to think about. You're given two envelopes. Each envelope contains a check for some amount of money. You're given that one envelope contains exactly twice as much money as the other one. Twice as much money as the other. But it's symmetrical. The envelopes look the same. You can't judge the thickness or anything. They look completely identical to you. It's symmetric. All you know is one of them has double of the other one. Okay? They both have some positive amounts of money. Okay? So you get to pick one. Well, so far there's not, pick either one you want. It's symmetrical. Let's just say you pick that one. Okay? Now you get, first assume you get to open, there are variations where you get to open it, variations where you don't. First assume you get to open it. Let's suppose you see $100 there. Then you're given the question, like in Monty Hall, do you want to switch? So you might reason, well, the other one, this one's 100 now. The other one could be 50, could be 200. Seemingly, those are equally likely. So if you average 50 and 200, you get $125, which means you should switch. Now, that argument did not depend on this being $100, though. So let's just call this one x. The other one is either half x or 2x. The average of half x and 2x is greater than x, so you should switch. But in that case, why bother even opening the envelope? That's going to be some value x. The other one on average is greater than x, so you should switch to that one. But then you should switch back, right? Then you switch forever. Then that's not good. All right, so have a good weekend.